finally, we are reached the stage to talk about the theta correspondence and dual pairs. Okay, so what is a dual pair? So a dual pair is basically a pair of subgroups in another subgroup, in another group S, say S. We call G and H is an abstract dual pair if G is a centralizer of H in S and H is a centralizer of G in S. Okay, so this is basically it's just a group theoretical definition, but this definition is in generally not good. Because we are actually looking at the algebraic groups or Chevalier groups or reductive groups. So we should consider the situation that S is actually an algebraic group and the G and H are algebraic subgroups. Actually, there should be closed subgroups inside S. So topological, algebraic group is an algebraic variety or algebraic variety such that it is also has group structure, and the G and H must be a closed up variety of S, and so you can define the centralizer of the H. This is again an algebraic group subgroup, closed algebraic subgroup of inside S, and you claim this subgroup scheme or subgroup variety is same as a subgroup variety of G. So later we will see what's the difference between the algebraic and abstract. So we require the actual requirement for the dual pair or algebraic dual pair is that this G and the H must be mutual centralizer in an algebraic group sense. So in this case, we will call G and H is an algebraic dual pair. Okay, so a specific construction is that if G and H are algebraic dual pair as F group scheme, or so it's a group defined over F. F could be a p-adic field or R or C, or a finite field. Then you can have a construction called extension of scalar. You can extend the field to so if K is the extension field of F, is an extension field of F, then you can construct a variety of scheme defined over K using the same polynomial equations, but you just view the coefficient of the polynomial equation in F as a polynomial with coefficient in K. In this way, you will get a, so in general, if you have a X is a F scheme, then XK is X with, I think it's a kind of extension of scalar. It will be a scheme defined over K. So in this way. So typical way is that, for example, X, you can think it's a real vector space of dimension n, then extension of scalar to the complex coefficient, it will give you a complex vector space of dimension n. Okay, so, but they have the same basis, basically, if you fix the basis. Right, so you were allowed to have this kind of construction for real and complex. So for the Archimedean field, it's not that important because you essentially only have complex number and the real numbers, these two fields. But for p-adic field, you have a lot of different extensions of the p-adic field. Also for finite field, it's also important because you have a lot of extensions. Actually, for each integer n, you have an extension, a unique extension of a finite field of degree n. Okay, so the warning is that algebraic dual pair does not imply that the F point of the algebraic group form a abstract dual pair. So there will be several different examples in GKT's book section 10.5. So do I need to explain what is F points for a scheme? No need. Okay, good. So I will give you an example, I think, somewhere. Right. So the one of the example is this one. So consider the field of F3, which has only 3 elements. Okay, so consider O11. This is the orthogonal group of size of signature 1 and -1. Okay, so then the group O11 over F3, the F3 points will be say 2 cross say 2. Is that okay? So O11 is a very weird group somehow. So for any field, let's say, it is actually F semi-direct product with the element 0, 1, 1, 0. Okay. So F is so it's generated by this 2 type of elements. So another type of elements is A inverse 0, 0, A inside F cross. Okay, so these are basically the structure of O11. Okay, so this part is isomorphic to F cross, and this part is isomorphic to say 2. Okay, and so but if F is F3, then F cross has just only 2 elements. So the group O11 F3 has 4 elements, and it has at least two order 2 elements. So then from the abstract group theory, you know that group has order 4 has only 2 possibility. Either it's a cyclic group or it's a Klein 4 group, which means it is isomorphic to say 2 cross say 2. Okay, so and this one you can have a clear identification is that you can think it is generated by this element. I think this one -1, 0, and right, and this one element 1, 0, 0, -1, I think. Okay, so you have another presentation of the group. Okay, anyways, this is O11 F3 is just a say 2 cross say 2, and so this. Okay, so later we will explain the general construction of the type 1 dual pair, and so you should consider is actually you take a symplectic space over the field F, and you take the tensor product V and W and V. So this one acts on a vector space V of dimension 2. So then it's obvious that so the space so W tensor V is basically W plus W, right? So one copy is, okay, so you can think V has 2 bases. One is E1 and another is E2. So it's V is a span of E1, E2, such that E1 is 1, E2 is -1, and E1, E2 is 0. Okay, So therefore, this space can be viewed as W tensor E1 plus W tensor E2. And okay, so say, so each one, so this one, each space is a symplectic space, right? So you can see that the centralizer, so O1 is just a act on this O1 just act on this space, and O1 also act on this space. So it will stabilize each space. So therefore, I think you can see that the centralizer of O11 inside the big symplectic space is actually two copies of SPW. So it's properly contains SPW. Okay, so that's the example that so although you will have a reductive dual pair or a dual pair, algebraically it's a dual pair, but its F points does not form a abstract dual pair. So so this problem will be resolved if the field F is be like not F3 but F9, then it should be fine. So it become a abstract dual pair already. So this is, in this case, it's just because O11 F3 is too small, so that its centralizer is larger than the expected centralizer. Okay, so right.
Sorry,
So we will.
can I ask a quick question?
Yes.
So is it true that if your finite field, your Q is sufficiently large, then you won't run into this problem?
Yes, you are right.
Okay. Okay, thank you.
Okay, so this is the only exceptional case of the finite field, actually. Okay, so right, we will consider also the so have a additional assumption in the dual pair is about a reductive, which means that the group itself is a reductive group. So which means that G and H are reductive group. So then it and the G and H form a dual pair inside the SPW, where W is a symplectic space defined over F, and the SPW will be viewed as an algebraic group defined over F. And I think for the theory works, let's assume the characteristic of F is not equal to 2. Okay, so this is by definition just algebraic dual pair G and H inside the SPW such that G and H acts on W reductively. Or I think it's also okay to assume that G and H are reductive group. So what's the meaning of G and H acts on W reductively? Means that this action decomposed into irreducible direct sums of irreducible representations. It means that the action is semi-simple. So in this case, G and H, okay, so moreover, we call GH is an irreducible reductive dual pair. If you have no orthonormal decomposition, orthogonal decomposition of the symplectic space in W1 as W1 plus W2, such that each module W1 and W2 are G cross H module. So this is the definition of irreducible. Okay, so later I will give you example of reducible reductive dual pair and irreducible reductive dual pair. So here's the explanation why you need the condition of reductive. So the simplest case is that you consider SL2 or SP2. Okay, it's a SL2 is just SP2. Okay, it's a symmetry group of the hyperbolic space, hyperbolic symplectic space. Okay, so then you consider G, it is a unipotent subgroup. Then it's a natural, it's easy to see that the centralizer or inside SP2 of G as an algebraic group is just the G itself. So you would like to rule out this case. So this G is just a unipotent radical subgroup. Inside SP2. So it acts on W non-reductively. Okay, so right, and then GKT spent quite a lot of time to talk about the classification of reductive dual pair. So it's essentially kind of invariance theory and linear algebra. But it can be quite tricky. So you have to know the theory of simple central algebras. Okay, so I will skip the proof but explain the result. So if suppose G and H is an irreducible reductive dual pair inside SPW, then you will have following two cases. The first case is called the type 1 case. So in this case, W itself is a simple G cross H module. Okay, another case is that it's called type 2 case. It means that W is as G cross H module is decomposed into two components. One is X, another is Y. And the X and the Y are both simple G cross H module. And the Y is isomorphic to the dual of X. So actually this X and the Y are totally Lagrangian. X, Y are Lagrangian of W, which means that X and the Y are both totally isotropic. Okay, so these are the two cases we call type 1 and type 2. Then the rest of the part is that let me see. So what is the general dual pair? General dual pair is basically direct sum of irreducible dual pairs. So if G and H is a reductive dual pair in SPW, then you will have a decomposition of the W space W as direct sums of symplectic space W1 to WK, and the G as product of space G1 to GK and group G1 to GK, and H will be product of groups I think should be H1 to HK, such that each piece is GI and HI will be a irreducible dual pair in SPWI. Okay, so this is a situation. So the example is like typical example is that so for example, if V is a W is a quadratic space, and okay, V is a symplectic space. then W tensor V, okay, is a symplectic space. And then this SP, okay, OW and the SPV is a quadrant, is a irreducible dual pair. SP W tensor V. Okay, so this is a typical example. Then you can build like a reducible dual pair. So example of reducible. For example, you have W1 V1 and W2 V2. So like this, then your W can be W1 tensor V1 plus W2 tensor V2. Then this one O W1 cross O W2 SPV1 cross SPV2 is reducible. Reducible dual pair in SPW. Okay, so this is a typical example. Of course, there's no restriction that you can switch the role of the V and the W. You can write this, and this one could also be a reducible dual pair. For example, it's like SPV2. Here you put OW2. Okay, so this is again a reducible dual pair. Okay, so therefore you see, to understand the general dual pair, you are essentially want to classify all irreducible dual pairs. So for the irreducible dual pairs, we also have a notion called so absolutely irreducible dual pair. So here is a situation that for algebraic group, instead of extension of scalar, you also have a restriction of scalar. For example, you can view a complex group as a real group. You can have a group defined over F cube. F9, say, view it as a group defined over F3. Okay, so the situation is that if you have a K, it is an extension field of F. If you have a irreducible dual pair inside, or actually if you have any dual pair inside SPW, where SPW is defined over the field F, you can do the restriction of scalar construction so that you will have a let me see. You will have a algebraic group restriction of scalar K over Fg. This is defined over F. This is a group over F. This is also a group over F. So you can restriction of scalar of the symplectic form. So this will be a symplectic space defined over F. So the form is given by, so this W restriction of, you can take the form just to be the, so you have a trace map from K to F. So you can define the form like restriction of scalar K over F W. The form is like it takes W1, W2 to the trace of W1, W2 of the original vector space W. So that it form a symplectic group of a symplectic space over F, then this will also be a reductive dual pair. So the question is that right, the question is that you see that especially for the p-adic group, you have a lot of group extensions, field extensions. So you would like to wish that this field you are considering is most economic. So we can define the notion called absolutely irreducible, which means that this a pair which is an irreducible dual pair in SPW, we say that it is absolutely irreducible if there's no other field, no non-trivial extension field K of F, such that W is given by the restriction of scalar from the K vector, K symplectic space, and the G and H are coming from the restriction scalar of G over K and H over K. So then in this case, it's called absolutely irreducible. Okay, so actually you have an alternative definition of absolutely irreducible. It is saying that a pair, if it is absolutely irreducible, if and only if the you can do the extension of scalar to the algebraic closure of the field. Then after you do the extension of scalar, it is actually an irreducible dual pair. So the irreducibility does not change after the extension of scalar. Okay, so the reason is that if you have a restriction of scalar, so you have this kind of fact that is that the restriction of scalar of K over F of algebraic group defined over K, and then you do the extension scalar back to K. So this one is actually just a product of G with the factor that for each, I think we can assume that K is a Galois extension, then maybe not really need, but I think so. It's like for any index I in the Galois group of K over F. So it's after you do the restriction scalar and then you extend it, it will just be the product groups. And then if it's not right, if it's coming from some restriction of scalar construction, then the irreducibility will be like violated after extend to the algebraic closure. Okay. Right. Okay, so right. I think where am I? Okay, so I need to go to the okay, so here's a fact that okay, you actually will have absolutely irreducible dual pair, but not abstract dual pair. So we have explained one example, which is the finite field case. And there's another additional example is that, again, the reason is that one of the group is too small. Is a case that D is a quaternion of the field. So this does not exist for the finite field. It's only exists for the local field, R and a p-adic field. For each such kind of field, you will have a unique quaternion algebra over this field, and we call it a D, and the D1 is a non-one set of non-one element. It can be viewed as the algebraic group of SP1D. So this is a algebraic group has a root system, okay, root system of type C1. Of course, C1 only have one point, but you choose to say it's type C1. Okay, and then it will pair with any O star D. This is so this is a group so reductive group with group system D any, let's say 2M, maybe Dn. Okay, so for this dual pair, again, it's again it is not an abstract dual pair. Okay, so this is because this is because the centralizer of D1 inside the SP. So it's actually you have a large SP2 and D. So this D1 is I think it's just SP2N. Okay, sorry, I'm not sure what is the centralizer in this case, but I'm sure that it is larger than this one. O star 2 and D. Right. Okay, so these are the two like exceptional cases. Okay, so maybe any question? No. Okay.
Sorry, Prof,
Yes.
what is O star 2n?
It is a quaternic group over D, so you can think it as what should I say? You have a dimension D. Okay, so you consider the space V. This is D. I think Dm. Then you put the put a skew Hermitian form on V.
Okay.
Then you take the right. You take the isometric group of this Hermitian form, skew Hermitian form. Then you will get O star 2n. Wait, it's symmetric or skew symmetric? I think you should take the symmetric Hermitian form on it, on Dn. So for example, you can take, so this one can be think as a collection of A1 to AN. So then you can take the pairing AI BI to be summation AI BI bar. Bar is the quaternic involution, principal involution on the quaternion. So the quaternion, so do I need to explain what is quaternion?
No, quaternion is fine. Yeah.
Okay, so then you have an involution on this. So you can take this form, and then the isometric group of this form will be right, O star 2n.
I
So
see.
as
So
a
you can basically think of it as a matrices that basically preserve that form, right?
yes, right.
Okay. Okay.
Okay, so right, let's come to the simpler case is a type 2 dual pair. So what are the irreducible type 2 dual pairs? So assume that, so class, I should write the classification of irreducible dual pair. Okay, so for type 2 case, it means that your space, so it will actually given by the following data. So you first fix a division algebra D over F, irreducible, absolutely irreducible, I think. You fix a division algebra D over F, it can be quaternion or it can be any arbitrary field extension of F. E and B. Okay. Sorry, I should say that it's just a division algebra. So right, it basically have two cases. So either D, so the simplest case is D equal to F, or D is equal to should I say absolute? Maybe I can delete this type 1, 2 irreducible dual pair. So, or D is a field extension of F, or D is so if is a skew field, so then over F, which means that it's not commutative. Then in this case, for if the base field is finite field, you don't have such kind of situation from the class field theory. And if it is base field is R, then you will have a quaternion. And if the base field is a p-adic field, then for each integer you will have division algebra attached to this integer. So you have a lot of choice of division algebras. Then you take a right D module of that called W and a left D module called V. Then you form the tensor product. So the tensor product will be an F vector space. And then you can consider the direct sum of F and X and X star, where X star is just the dual space. So it's a home X to F. Okay, so there will be a natural pairing between X and X star. And the symplectic form is given by X, Y, X prime, Y prime is given by X, Y. Actually, it's Y prime X minus Y X prime. Okay, so this is the symplectic form. It's a symplectic form on W. Okay, so then G will be just the general linear group of the right D module W, and the H will be the isometry group of the left D module V. Okay, then this G and H will X on X and X star. Okay. So therefore this will be a commuting action on X. So X itself is an irreducible G cross H module. And X star is a dual of X, is also irreducible. Okay, so it's a representation theory, not over complex number. It's a representation theory over a field F for group or defined or algebraic group defined over F. Okay. Right. It's essentially just linear algebra. Okay, so this is a type of irreducible dual pairs of type 2, and it is absolutely okay. So it is so this case. So remark is that it is absolutely irreducible if and only if the center of D is just F. Okay, so which right, that's it. So essentially, for example, you will have a dual pair GL K M GLMK if K is viewed as an extension field of F, but it's this one, if K is a genuine extension of F, then it's not absolutely irreducible. So you study the just from a representation theoretical view point of view, if you study the representation of GLNK, is saying a study of the restriction of scalar of GLNK to F. It's the same. But from long length point of view, I think you will have different space of long length parameter if you view this abstract group GLNK as a K group or as a F group. The space of long length parameter are different. So it's typical to study like the branching problem of GLNK representation restrict on GLNF, this kind of stuff. Okay, right. So this type 2 is very simple. It's because it's basically the dual pair just formed by general linear groups. They are just matrix groups. Okay, so the type 1 case is also actually simple. In this case, the W itself is tensor product of two spaces. The construction is like if G and H is a subgroup of SPW and it is an irreducible reductive dual pair of type 2, if only if there exists a division algebra and with the involution tau. Notice that this tau can be identity map. Okay. Such that the center of D is called E, is contains F, and such that E contain E tau. This is a tau fixed vectors also contains F. So the involution on F is trivial action. And you will have a negative epsilon Hermitian space W over D, and the Hermitian means the Hermitian with respect to the involution tau for some epsilon in ±1, and a left epsilon Hermitian space V over D tau, such that this W is just the tensor product of V and the W. And the G is just the isometry group of this form. And the H is the isometry group of the form on V. Okay, so furthermore, G and H is absolutely irreducible if and only if the tau fixed point in the center of E is equal to F. So here's, so it's quite abstract, but let me do it more quickly, and so this is the only table you need to memorize. Okay, so this is a table of absolutely irreducible type 1 dual pairs. So the first case is that D and E and F are the same. And the involution is, of course, the identity, the trivial involution. And if epsilon is plus, then V is, okay, so epsilon is plus, then V is a quadratic space. So UV is just the orthogonal group. And I think, right. So W, in this case, W is a symplectic space. Okay, so, right. I think I should put it here. So in this case, W is, so W symplectic. Okay, so this one is that epsilon is -1, then V is symplectic and the W is orthogonal. And another case is that D is just a quadratic extension of F. And the tau is just the canonical involution on the quadratic extension. It's a Galois involution on the quadratic extension of F, non-trivial Galois action on the extension field. And E, I think this typo. E is properly contains F. I think F is equal to E tau. Okay, so in this case, if epsilon is plus, then it's a Hermitian space. V is a Hermitian space. I'm sorry. I think I should go this way. I think my mistake. Sorry. So the quadratic extension case is this one. E and E is a degree 2 extension of F. Tau is a Galois conjugation, then in this way, E tau is equal to F. And so if epsilon is plus, then it's a Hermitian space, and the group is a unitary group. If minus epsilon is minus, then it's a skew Hermitian space, and the isometric group is again a unitary group. So it's the inner form of the type A group. Okay, there's another case is that when only happens when F is a field. So F is either R or p-adic. Okay. And also I think non-local Archimedean, right? P-adic or other non-local Archimedean field. Non-Archimedean local field. Okay, so in this case, you will have quaternion. So this is a quaternion. And E is the center of the quaternion. It is equal to F. E is the center of the quaternion. So this is F. And the tau is a canonical involution on the quaternion. So the quaternion has basis ijk, and the involution will send I to minus ij to minus jk to minus k. So right, quaternion, you view it as a vector space over F, then it will have basis 1 ijk, send 1 to 1 I to minus ij to minus jk to minus k. Okay, so you have this involution. And then you will have, when the sign is plus, then you will have quaternion symplectic space. And then when sign is minus, you will have a quaternion orthogonal space. Okay, I think I made a mistake before, so someone asked me about the definition of O star. Here you should take the skew Hermitian form. Right. Here you should take the skew Hermitian. How do I get a skew Hermitian form? I think it's fun to just multiply I. Okay, so it's okay to just multiply I, A, I, B, I bar. So this is skew Hermitian. Okay, let me think about it. I will give you the answer next time. Okay.
So,
right.
The theorem you mentioned that it's a division algebra.
Yes.
So it's always quaternion or it could be arbitrary.
Oh, okay. So if you only want to classify irreducible dual pairs, then it can be arbitrary division. It can be non-quaternion. But if you require it to be absolutely irreducible, which means that the simplest way to define it is that you assume that after field extension, after base change to the algebraic closure, it's still irreducible dual pair. In this case, then it must be division, the quaternion.
So that as a correlator, B has to be quaternion as well.
Yes. So because I think I can do the example is that this is the simplest example is that if you have sp2 and C and you view it as a real group, 2MC and OMC, you view it as a real group. It is the dual pair over SP 2MN R 4mmR actually. This is actually a non-irreducible, non-absolutely irreducible dual pair. Because this space is so it's a C2N tensor over C of the Cm. So this is C2MM. So you do the restriction of scalar. So this is R4mm. Okay, so then you do the base change. So you will to C, you will get so base change to C. It will give you sp2nc cross sp2nc OMC cross OMC inside the sp4mnc. So this dual pair. So this is not irreducible. So this is because this dual pair is essentially from a dual pair over complex number. So for the classification reason, you only consider the most simple case.
In this theorem, that you need the F is a local field or
I think for this theorem, it can be arbitrary field.
So but the table 1 is
for local field. Yes. Or I think for finite field. Finite field, of course, you don't have this case. Okay, so right. I think maybe let's have a break, then we continue. Let's have a 10 minutes break. Any question? Okay, let's have a 10-minute break. Other discussion. Oh, cool. So before we go to the actual definition of dual pair correspondence, we have to address the one technical question is about splitting. Actually, the whole book of GKT spent 400 or 500 pages on the splitting. All the work is about this splitting. It's very technical but it's actually very important. Okay, so we know that MPC1 acts on the metaplatic group and the symplectic group acts on the wave representation, and the symplectic group does not act on the wave representation. So it would be a good question that if we have a subgroup inside SP, whether say G and H, these are two subgroups of SP, whether these two the actions split. So on this when restricted on the subgroup. So for the type 2 case, the answer is yes, because so the dual pair is like G and H. This is GLDX and GLDY. So GLDX and GLDY is actually can be considered as a subgroup inside GLX tensor Y. So recall that our space, symplectic space is X tensor YD plus X tensor YD due. So this is X tensor Y and X tensor Y star are both totally isotropic. So they are Lagrangian. So this one actually goes to the Siegel parabolic of X tensor YD, right? And when restrict on the Siegel parabolics, the covering splits. Splits means that there exists a group homomorphism from SP to MP. So therefore, you can pull back the wave representation to view it as DX cross GLDY representation. Okay, so this is for type 2. So the message is that always split. For type 1, it's not always split, but almost always split. Recall that we have the classification, so we can assume that the type 1 dual pair is formed by minus epsilon Hermitian space over D and epsilon Hermitian space over D. And so that this symplectic space W, big symplectic space is W tensor D over V over D. So in this case, so you will have, certainly you will have a map from GW cross HV to SPW. The question is that whether you can have a dashed map from GW to MPWC C1 to make this diagram commute. So the answer is that the splitting always exists except for the following two cases. Okay, so I assume that F is RC p-adic and finite field. So for finite field, it's always the splitting always exists. Actually, for finite field case, you don't need the mathematic group to define the wave representation. The wave representation is actually a symplectic group representation. Okay, finite field with characteristic of F is not equal to 2, I should like to say. Right. So, but there's exceptional cases is that F is R or p-adic field, and the space V is an odd orthogonal group. In this case, you cannot find the splitting. Okay, so there's a lot of computations about the explicit splittings from GKT's book of chapter 11 to 12, but in practice, it's fair to think about a group called the G bar. In general, if the splitting exists, it's just a GW. Okay, it's just an algebraic group, or it is a metaplatic cover if split does not exist. Okay, so all the splittings are classified in this way. So basically, you need a character for from E cross to C1 such that chi restrict on the norm group of E cross is equal to the I'm saying. Okay, so there will be so this one restrict on F cross is the character defined by the norm. Okay, so this is a unique quadratic character from F cross to so this is a unique quadratic character given by this one of E cross goes to. So this one is actually isomorphic to plus minus 1. Okay. So there's a quadratic character with respect to the quadratic extension E over F. Then you require that this chi restrict on F cross is seen as this quadratic character. This is a chi. It's a part of data if you want to split the action for the unitary dual pair. But in general, this chi you just put it's a trivial character. In other cases, then the message is that basically from the Schrodinger model, as a Lurie invariance, this kind of Lurie cocycle, you will have a canonical splitting, which is a continuous group homomorphism from G bar. Notice that the G bar is either GW or the metaplatic 2 cover, depends on situation, to the MPW tensor VC1. Okay, so this splitting is only depends on chi. Okay, of course, in its construction, you have to choose a polarization, but after quite hard work, you will be able to show that it's independent of all these kind of choices. And we call this splitting the Lurie splitting of GW in the metaplatic group. And this data will be called the Lurie splitting data. So for other splittings, it will basically be a character twist of GW, because GW is in general not a semi-simple group. It will have center, so you can have characters, non-trivial characters of this GW, this group, then the general splitting will given by chi psi alpha. Okay. Right. So this is some comments on the splitting. So, right, then we can start to talk about Howe duality. Yes.
What's the dependency on this kind of stuff? I suppose you have many choices. Right?
Yeah, you have many choices. Basically your psi can change. It's like if you replace psi to a psi, then this chi will be a square chi, something like that. Yes, and alpha is the arbitrary character. All the splittings are given by the canonical splitting times character of SW.
And your chi is also like almost.
Chi is, you have a lot of choices actually. You only require that it's restricted on F cross is same as
yeah, so this is for the local field.
Yeah, this is for the unitary group.
So it's
for orthogonal symplectic, you don't have such kind of ambiguity.
But if you have a different choices,
yeah, it will give you different splitting.
How it matters.
Yeah, that's why GKT is so sick. Okay, they have a whole chapter discuss this problem.
The alpha again.
Alpha is just a character of GW. Yeah, no arbitrary character, no need to add C character. So yeah.
C character basically is only for the unitary, right?
No, orthogonal group you also have.
Orthogonal group is a plus on the right?
Yes, plus minus. Yes.
The unitary could be arbitrary.
Yes.
The central character. This is the central character.
Right.
So basically, eventually, if you have the local lines correspondence, the whole local lines correspondence is this is like the auxiliary data.
Yes, you need this kind of data to discuss the theta correspondence somehow, especially the you need some kind of splitting so that you can talk about the.
Have you go through the chapter 5 for the BS?
You mean in my talk? No, I don't.
Yeah, we can talk about it.
Okay. So let's discuss some definition, the basic definition of Howe duality conjecture, or Howe duality or theta correspondence. Basically, we take a reductive dual pair in SPW, or maybe I should write this. Okay, then you can do several different versions. So one version is that you take say this is a recall that this say is a subgroup of C1, then you can consider MPWC. This is just a say extension of SPW, such that the metaplatic 2 cover is inside this group. Okay, so then for arbitrary group G inside SPW, you can consider G tilde. This is just a preimage of G inside the covering. Okay, so you can start to talk about the class of genuine representations of G tilde. This is just irreducible representation of G tilde such that the center act by scalar multiplication. Okay, so this is a set of genuine representation. And then the Howe conjecture or Howe's duality theorem saying that if F is a local field of characteristic not equal to 2, then for any pi and pi prime, both are genuine representation of G and G tilde and H tilde. So you first you have a weak version. This was proved by Li and Sun and Tian, which says that the multiplicity of pi 1 times pi 2 occurred in the V representation attached to a character psi is less than or equal to 1. Okay, so basically in this setting, we have G tilde cross H tilde. So this is not an embedding because the center always will map to center of G tilde and the center of H tilde will be mapped to the same element, same set. So MPWC. So you know this will map to the endomorphism of V representation. So you can pull back the V representation to view it as G cross H tilde representation. And the point is that this home space has dimension at most 1. It turns out the proof of this one is not very difficult. You need some kind of custom Gilfan custom argument. So this is a 8-page Invencioni paper. Okay, so this is called a weak Howe conjecture. I'm not sure whether this has established for the exceptional dual pair. I'm not sure. I don't know. Probably not. So yeah, I guess.
Even for this classical case, like the finite field case is not true.
No, it's not true. Right. Wait. So the finite field case, it's true. Multiplicity is less than or equal to 1. Yes, it's multiplicity. Yes.
Because like in the GGP case, it's not true. The GGP for finite field case is not true. Yeah, I mean for the branch.
Let me see.
For the generic, it's true. For the.
Oh, okay. So it says that to give you arbitrary representation, pi and pi prime, each tensor product exists has at most multiplicity at most 1. It does not say that the big theta is irreducible.
No, yeah, I only say the restriction law is if you order finite field, this is basically a branch law.
Yes.
So,
Uh,
I think because some smaller representation that most is not one.
okay,
For the cascade or generic one is true. But for some very small representations.
wait,
Because I remember
maybe you are talking about a GLN case, or you're talking about the type 1 case. type 1.
And
I think let's type 1 case. I think type 2 case may have problem. I think type 1 case this should be fine.
Probably the functional fluid characteristic too. You also conjecture this is
I don't know. You always ask tough questions.
For exceptional, is it I mean, I thought it's almost done already by that last Invenciones paper by Savin and Wittek.
Oh, really?
I don't know. I'm not sure about the exact details, but I thought so. I mean,
Okay. I never checked. Maybe I should check and come back to you later. Okay. Right. So the original version of the Howe duality conjecture, it's actually not that original, is that we consider for arbitrary representation pi and right, I think I still should write pi and pi prime maybe. Here I write pi and pi prime. Okay, for arbitrary representation, irreducible genuine representation pi, we can consider the tensor product of wave representation with its conjugate. So notice that the conjugate, the center actually act by say inverse. So if you multiply them together, the center, the say part action will be trivial action. So the action, total action on G star, G tilde on this space is just a descent to the G action actually. So you can take the G isotypic maximal G isotypic quotient, G equivalent quotient. So this one will be a G H tilde module. With H tilde act on the wave representation part. Okay. So the fact is that this module is actually a finite length module, and you can consider the maximal semi-simple quotient of this big theta pi. We call it the small theta pi. So a priori, this small theta pi is just a semi-simple representation. Okay, so this is a modern way to define big theta pi. But if you look at Roger Howe's definition, it actually defined in this way. It says that the wave representation quotient of the insertion of the all kernels of the intertwining operator from wave representation to pi. So it is actually isomorphic to pi tensor big theta pi. Okay, so this is the maximal pi isotypic quotient of omega. Okay, so you have a quotient map from this one to this one, and this is maximal pi isotypic quotient. And you can show that, so this representation will be isomorphic to pi tensor something. And this something is actually naturally isomorphic to the definition here. So it's not completely trivial, but it's not very difficult. So to show that this you have this kind of structure. Anyway, you can consult the GKT's book. Right.
In this way, especially for the Archimedes, it's a reference. Like you need to consider wave Howe space.
Yeah, you.
All of the last even find the intersection of the kernel.
You can define the so GK module version in the same way.
Everything instance of the GK module.
Yes.
And then do the
yes. So otherwise, you are right. You should put the topological tensor product. Otherwise, it
This intersection is obviously like closed and the customer.
yeah, intersection of closed set is a closed.
I mean, the kernel of the team, the team specifically.
The smooth, yeah, smooth homomorphism. Yeah.
So then you take the omega and the pi, those are the
Right.
customer.
Yes. Omega is a Fresher representation. Yes. And the pi is a Kasman-Waller representation. You can, right. Let's be not so strict on the topology. Okay, right. So the Howe conjecture or the theorem is saying that this big theta pi is actually has a unique irreducible quotient. In other way, it says that the small theta pi is actually not only semi-simple but irreducible if it's non-zero. And furthermore, if I think I should say that if it is non-zero, if it is non-zero. Okay, so right, another part is saying that if pi and pi prime has the same theta lift or small theta, then pi and pi prime are the same. So it means that this lift is an injection map from its domain to its image. Okay, you actually can reformulate as commented in the KT's book that 1 and 2 is equivalent to saying that the dimension of small theta pi, the home between small theta pi and the small theta pi prime is less than equal to the dimension of home from pi and pi prime for arbitrary irreducible representation and pi and pi prime. Okay, so you have so recall we have mentioned the splitting. So in application, we actually do not somehow like the covering group G tilde because eventually this G tilde is a split covering, right? In the most of the case. So recall that G is either split in this covering or G tilde is just a metacritic covering. So recall that G bar is just a G if it's split and the metaplatic to cover if it's not split. So anyway, the splitting will actually give you G bar cross H bar. You define a similar way for the H bar to the metaplatic group. And so you can consider irreducible G bar. This either is just an irreducible representation of G or it's a genuine representation of the metaplatic 2 cover, which means the center act by plus minus 1. Okay, so the plus minus central extension part plus minus 1 act by plus minus 1. So you consider this set, then you can reformulate Howe conjecture in the way that you define the big theta to be the wave representation tensor pi check. So for irreducible representation in the G bar, okay. And then this big theta pi, small theta pi is just the maximal semi-simple quotient, and the Howe duality is just this formula as what I said. So it's basically said that if you have a splitting, so you can consider representations which are correspondence either between the actual algebraic groups and or algebraic group, orthogonal group, odd orthogonal group with the metaplatic 2 cover. Okay, so in general, the point is to ask. So this theorem was proved by Roger Howe for the Archimedean case, was Poget for the p-adic case when p is not equal to 2 power, p is not equal to 2, and the Mingus for the type 2 dual pair, and the Gan Takeda and the Gan Sun for the type 1 dual pair. Okay, so it relies on a lot of things somehow, especially Gan Takeda's proof relies on some structures about the, I don't know, induced representations, and so their method is based on Mingus method. Well, okay, so this after the duality conjecture be proven, so you should ask us, I think it's fair to ask this following three questions. The first one is when this big theta pi is non-zero. It turns out this condition will reflect the properties of pi. And also, the question is to describe the small theta pi. So for this question, I think in many cases, this is known. For example, for the p-adic case, nowadays, you can describe the small theta in terms of long length parameter. And for the Archimedean case, I think for equal rank case, you have the result. For non-equal rank case, you have no result, no general result. Okay, so then you also can the Hesse diagram of the big theta as a module. So yes, right. So this one is known. Known when pi is trivial. So in this case, big theta is a submodule inside the general principal series. Pi is unipotent. Some cases, not the very general, not the general cases. So, but when pi is trivial and the V is split, so this is that the theta pi is a sub of degenerate principal series. Okay. So for this you mean when pi is trivial, theta pi always non-zero.
I mean the theorem 13.21.
It's less than equal, right? If it's zero, this is just zero. Not equal. Yeah, here. Okay. Right. So I would like to say that for the first question, it's actually there's a very important phenomenon called the first occurrence index, the conservation relation. So I would like to explain what is the first occurrence index. So we should consider a width tower. So what is a width tower? If you have a formed space V1 and V2, we say they are in the same width tower. If you can add something hyperbolic space so that this on V1 and V2, so that makes these two spaces are isometry to each other. So you have a more precise, more concrete construction of the width tower is that you first fix an anisotropic epsilon Hermitian space, and you keep adding hyperbolic space on the space. So therefore, on VA. So therefore, you will have a chain of epsilon Hermitian spaces. Hyperbolic space means a two-dimensional vector space with a form that it has spaces E and F, and the pairing between E and F is equal to 1. Pairing E with E and F with F is 0. So H is the span of E and F, and E equal to FF equal to 0, EF is equal to 1. So these conditions characterize the hyperbolic space. So you keep adding the hyperbolic space, you get the width tower. And so there's an important theorem, not very difficult to prove. but still technical, is that non-vanishing in the stable range. If your space, so you are allowed to consider W, G bar W with and a representation of this, and you want to lift it to H bar VA plus HR, okay, to this group. So you consider this dual pair, and you consider representation lift to the representation of H bar. And the answer is that when R is greater than equal to the dimension of W, this is called a stable range, then the big theta lift is non-zero. Okay. Right. So basically, this is because the restriction of the Weyl representation contains the regular representation of G bar W. Or actually, not contains, has a quotient which goes to this one. Okay, so if you are interested, you can read GKT's book. Okay, so you also have right. So this is a one fact, but we also would like to see how we would like to let this R change to see different liftings to for the same representation pi here to different groups. Okay, in this case, we need to consider the situation. So this one, this VA plus 2R is by definition just VA plus hyperbolic space. Okay, so A plus 2R is just a dimension of the vector space. Okay, so then somehow we need to fix the splitting, and we also require some compatibility between the splitting. So we say that the different splittings from G bar W to MPW tensor V plus 2R is a compatible set of splitting if it fits in this commutative diagram. It basically you have this one and this one. So because W tensor V A plus 2R plus 1, you can think as W tensor V A plus 2R plus W tensor H. So therefore, this one is can be viewed as a subgroup of the multiplied group above. So you require the following commutative diagram so that you can compare the non-vanish or the result of the splitting, result of the lift. Okay, so assume we have a compatible system of liftings. So the obvious choice is you just take the Larry splitting. They are compatible with each other. So this is also proved in GKT's, which I think never be written carefully in the literature. Okay, so you have something called the persistence principle. So suppose you know that the lifting is non-zero for certain R. Assume that you have a set of compatible lifting. So then we can, okay, then if you have non-zero for certain R0, then it will be non-zero for any R bigger than R0. So the picture is that, okay, I should be quick. So if you have pi, if it's lifted to somewhere V0, VA plus 2R0 is not equal to 0, then above all above, lift to all above spaces will be non-zero. Okay, so therefore you see the lifting pattern is that at certain stage, it will be non-zero, and below this stage, it will be all zeros. Okay, so therefore it's fair to define the first occurrence index. It is just a minimal dimension of the space, such that theta lift is non-zero. Oh, yeah. So I will finish. Let me give the last line about the conservation relation. So the previous stable range always has lift is can be rephrased as this one. So basically say the first occurrence index is less than or equal to two times of dimension of dw plus the dimension of the anisotropic kernel of V. Okay, so no.
So if the W is
It is orthogonal.
V.
Yes. Okay, so you have a sign representation. Actually, the first occurrence is of orthogonal group is 2 times dimension of W. And the conservation relation, which was pointed out by Kudla-Rallis, and they also prove it for the Caspidal representations later settled by Sun and Zhu for the PID case. So for the local field case is that, so this is a typical example. The first occurrence of index for pi and the pi tensor sign representation, if you add them together, it's equal to 2 times of dimension of W when pi is irreducible representation of the orthogonal group. Okay. So I'm going to talk about more about the first occurrence later, maybe. So I think that's all for today. Thank you.